If I start with one pile of money and I add to it a second pile of money, we finish up not with two piles but with one pile whose size depends on the size of the original two piles.
Similarly with forces. If I start with one force, like the tension of this spring pulling on the brass object, and I add a second force by putting on a second spring,
the combined effect is one force which depends on the size and direction of the original forces. We call this force the resultant force.
Because it only makes sense to add two forces together if both forces act on the same object. Unlike with money, which is a scalar, when we add forces we have to take account of the direction. If both forces are pulling in the same direction, finding the resultant is easy. We just add up the number of newtons for each force. If the two forces are pulling in opposite directions, that's still quite easy. You just have to take one of the forces away from the other one. The problem comes when the forces act in different directions, such as this, or this, or this. In cases like these, when we find the resultant, we must take account of the direction of the forces. And to do that, we need to use the properties of vectors.
Force is a vector, and vectors have both size and direction. This means we can represent vectors by drawing an arrow, where the length of the arrow represents the size of the vector, in this case how hard the force is either pushing or pulling, and the direction of the arrow gives the direction of the vector.
In this situation we have two forces acting on an object. We have 75 newtons acting to the right, we have 50 newtons acting upwards, and what we want to do is we want to find the resultant of these two forces. And we're going to do this by means of a vector diagram and scale drawing. So before we can do a scale drawing, we've got to choose a suitable scale. And to make best use of the paper, I think a good scale to use would be 2 millimeters, representing 1 newton. These arrows on the question, by the way, they're not drawn to scale, they're just showing where the forces act and what direction they're in. Now the next thing to decide is whereabouts on the page to start our diagram. If we look at the forces, we see the forces go up and to the right, so it makes sense that we start somewhere down in the bottom left hand corner of the page. So this would be a suitable starting point here. Now the next thing to decide is which of the two forces we're going to deal with first. And we can choose either. I'm going to deal with the 75 Newton force first. So I'm going to draw an arrow to represent the 75 Newton force. So if it's 75 newtons and 2 millimeters for every newton, I need to draw an arrow that's 150 millimeters long, going in the direction of that force, so an arrow to the right. 150 millimeters long. Which takes us to there. And the direction is very important, so I draw an arrowhead on the end of the arrow, making sure that the head of the arrow is within the length I've measured. I'm going to label that as 75 newtons. Having drawn the first force, I now need to draw the second force. And what's very important is I draw the second force from where my first arrow finishes. So from the head of the arrow there. So it's 50 newtons, so using the scale, 2 millimeters for 1 newton, I need to draw an arrow that's 100 millimeters long, and I need to draw it in the direction of this 50 newton force. So I need to draw it straight up the page. So it takes me to there, and I put on the head of the arrow to show that it's an upward force. And I can label this as 50 newtons. So I've drawn the two forces in turn. I want to find the resultant. In other words, we want to find what do those two arrows give us when we combine them. And combining those two arrows, they take us from this starting point, which was when there wasn't a force, and they take us over here. So the actual resultant is the arrow that takes us from the beginning to the end in one direct move. So I draw the arrow from the beginning to the end, put the head on the end of the arrow, and this arrow here represents the resultant. So to find the value of the resultant force, all I need to do is measure the length of the arrow. So that's 180 millimetres long. The scale is 2 millimetres for 1 Newton. So my resultant force must be 90 newtons. As we'd expect if you had together a force to the right and a force upwards, the resultant force goes upwards and to the right. We can find the exact direction of it just by measuring the angle. So if I put the protractor on there, I read the angle, it's 34 degrees. And we can check that that makes sense. Look at the two forces. The horizontal force was bigger than the vertical force, so we would expect that the angle here would be less than 45 degrees. So our result does seem to make sense. When we're dealing with vector diagrams, it's very important to remember that in the case of this force diagram, distance on the force diagram represents force. And that means that distance on the force diagram does not represent distance in the real world. And that means that different points on the force diagram don't correspond to different points on the object or to different places in the question. The only thing on this diagram is the forces, and all the forces in the question are all acting at the same point on the object.